Okay, so let's start the first lecture of today. I'll tell you some basic facts about Gaussian process models and how we can use these models to perform Bayesian optimization, which is quite important topic nowadays because it can be used, for example, for neural architecture search and hyperparameter search for different machine learning models. And so this is the outline of today's talk. My name is Evgeny Burnaev. I'm from Skolkovo Institute of Science and Technology. And so let us discuss how we can construct various quite flexible models using Gaussian processes. So first, some motivation. We would like to learn a scalar function, f of x, of vector x. And we have a sample of input and output vectors, xi, yi, a sample of size n. Actually, in practice, there are a lot of various applied problems like regression problems when you model predictive control or you do some optimization problems in engineering or in case of robotics applications. In all these cases, we need to be able to efficiently model a regression function. Besides that, we also can use that regression model as a latent model for classification. And so what we want, we would like to have some flexible model to construct regression. And at the same time, we need some mechanisms to automatically select model complexity depending on the sample and automatically avoid overfitting. At the same time, there are a lot of applied problems like the one depicted here, where we need not only to make predictions, but we also need to estimate uncertainty of those predictions. For example, as input here, we consider various technological parameters of a production of one batch of, in this case, it is sugar. And the output Y here consists of costs, losses, and efficiency. And we use historical data to construct predictive model how these losses, costs depend on technological parameters. And if with this model we predict that for some particular setting, profit will be like 40, and for other setting, profit is 60. But because if we are able to predict that the uncertainty for the second case is significantly bigger, of course it's better to select the first setting of technological parameters because it is more robust and it will be better for more stable production. And so with this simple example, we see that it's very important not only to predict output, but also to estimate uncertainty of that prediction. Another example why we need uncertainty is related to optimization. Very often we need to optimize complex black boxes. And even one calculation of black box value can be very time consuming and computationally intensive. And so we only have some set of points. And the only thing we can do is to approximate the real dependency realized by that black box with some regression model. And using that regression, we can select candidates where possible optimum is located. But actually, we should try to find that optimum not only in those points where the prediction is, in this case, low, but also we need to consider those regions where the uncertainty estimate is big, because possibly in those regions even a lower value of the black box function can be found. And because of that, we need to sample in those regions to reduce uncertainty, and possibly we can find there something interesting. And this is another example why we need uncertainty estimates when we perform so-called Bayesian optimization. And so the question is, Gaussian model is very simple. Whether it's really possible to use so simple distribution and at the same time to model some complex phenomena and construct meaningful, flexible, accurate predictive models. Actually, one of the most important formulas which we will use throughout this lecture is this well-known property of the Gaussian distribution. So the idea of this property is very simple. We have some multidimensional Gaussian vector here, and we divide this vector into two subvectors, subvector f1 and subvector f2. According to this division of the Gaussian vector into two subvectors, we in the same way divide the mean vector of the Gaussian distribution into two subvectors and the covariance matrix of this Gaussian vector into four submatrices. This, for example, this submatrix correspond to the cross covariances between components of the first subvector and the second subvector. And so it can be proved very easily that the conditional distribution of the first compound of the first subvector given the value of the second subvector, the distribution, this conditional distribution is Gaussian, and we can explicitly find conditional mean, conditional expectation of these conditional distribution and conditional covariance matrix. And so here we have these explicit formulas, and we will use these explicit formulas in our lecture when we will construct predictive models for the regression. And so let us talk about the Gaussian process model and how we can use it to obtain predictions in different settings. First of all, in order to construct any regression function, we need to have some assumptions about the class of functions. And actually, the simplest class of functions is linear class of functions. Also, we can consider, for example, polynomials, or we can impose some more complex constraints on class of functions. For example, very typically in statistics, they consider smoothness classes like Sobolev type classes, and Sobolev type class or Lipschitz type class, they are defined like this. So Lipschitz functions are those functions which fulfills this inequality where L is a some given constant. However, in case of Gaussian process regression, we don't use these deterministic assumptions on class of functions, but we consider some Bayesian prior assumptions on how function behaves. And so these prior assumptions can be formulated as follows. We assume that our data is generated by some continuous stochastic process. So all my pictures will be mainly in one-dimensional case. But of course, in general, we consider stochastic processes with index, which is some multidimensional input belonging to some input domain. And so we assume that our function actually is a stochastic process. It is a trajectory of some stochastic process. So x, in this case, x in one-dimensional case, x can be interpreted as a time, but in general, x is a multidimensional vector. And so f of x is some stochastic variable. And so for different values of x, we get some random values. We assume that there are a sample of m points, and we observe at each, and this sample of m points, it is fixed and deterministic. And we assume that for each point from this set, we observe f of xi, value of this stochastic process, at the corresponding sample point. So f sub I is equal to f of xi. And so these are our observations. And in order to impose prior assumptions on the function, we assume that the function we would like to recover from noisy data, this function is actually the trajectory of the Gaussian process. And according to the definition, that means that for any fixed set of input values and the set of corresponding output values is a Gaussian random vector with some mean value and some covariance matrix k capital. This is the definition of the Gaussian process. And the second assumption is that values of this mean vector is given by some deterministic function mu of x. In many of our, mainly in applications and in examples throughout the lecture, I will consider the case when mu of x is equal to 0 for simplicity. But of course, in different applications, you can set mu of x equal to some deterministic function. And the second assumption is that we assume that the covariance matrix is fully defined by some covariance function k. Actually, this covariance function also can be interpreted as a kernel function. I guess all of you know what is kernel trick and reproducing kernel Hilbert spaces, so this is exactly the same thing. This k is a kernel function that is a function of two arguments xi and xj, and by selecting a priori some kernel function k, we impose prior assumptions on how the trajectory of the stochastic process can look like. And so we assume that all values of the covariance matrix k capital is defined by this covariance function, which can be interpreted actually as a covariance between any two values of the stochastic process at any 2 points x and x prime. And here I just depicted the trajectory of the Gaussian process in one-dimensional case, and this is the trajectory of the Gaussian process in two-dimensional case. And in order to generate these trajectories, I first selected some particular covariance function. Then I defined some set of points in input domain. For example, in this case, I just considered the grid, quite a dense grid. And then I generated the Gaussian vector with Gaussian distribution. With zero mean and the covariance matrix given by the selected covariance function. And that's it. And then I just depicted generated values of that vector and obtained this picture. And so by imposing some smoothness constraints on the covariance function, we can at the same time impose smoothness constraints on the trajectory of the Gaussian process we can generate. And actually, this is a particular example. the covariance function, which is very widely used in applications, so-called squared exponential kernel. Of course, it contains some parameters, like parameter r sub I, or which defines a scale, and parameter sigma, which defines a scale of variations. So actually, if we generate a trajectory of a Gaussian process with a covariance function given by this formula, with different values of sigma, then the bigger value of sigma is, the more variable the trajectory we will obtain. So this parameter is responsible for the scale of trajectories. And when the scale is fixed, if we generate trajectories of the Gaussian process with different values of the scale parameter r, then depending on whether the scale is small or big, we will get either either not smooth trajectory or quite smooth trajectory. And it's quite obvious why we get such results, because if r here is small, that means the scale on which values of the stochastic process significantly depend on each other, this scale is small, and only on small scales values of the stochastic process will be similar. But and because of that, on bigger distances, values of the stochastic process differ from each other significantly. And so, because of that, the corresponding trajectory isn't smooth, and vice versa. So we see that by defining covariance function in a specific way and selecting its parameters, we can obtain trajectories of the stochastic process with different properties. And of course, we can consider more general cases of covariance functions. For example, in this case, I add here some parameter alpha, which is responsible for the degree of differentiability of the corresponding trajectories. And if I generate trajectories for different values of parameters of the covariance function for different values of alpha, we see that if alpha is small, if the parameter alpha is small, these trajectories will be very, very rough, not smooth at all. But if alpha is quite big, then trajectories are quite continuous. And so that means that we can model different prior assumptions on the function which we would like to recover from data. So that means that instead of imposing some hard parametric constraints on the function we model, here we use some probabilistic prior assumptions which we impose in the form of covariances. And of course, we can consider there exist a lot of other covariance functions, like the one is given here, which is a periodic covariance function. So I just insert inside the exponent squared value of the sinus function, and with such covariance, I can easily model periodic processes, and this can be useful to model periodic functions, or to model periodic time series, right? And so, moreover, I can compose different classes of covariance functions by combining existing ones. So I can sum covariance functions, I can multiply covariance functions, I can calculate convolutions of covariance functions. And in this way, I can obtain very complex types of stochastic processes with different properties in different locations of the input domain. And actually, there exist some automatic libraries like the automatic statistician and others, which automatically try to adapt the covariance function by greedy search to the existing properties of the data set. For example, whether the data set has some periodicities or some linear trends or non-linear trends. So depending on all these things, some greedy search engine inside the library, it tries to combine different types of covariance functions to better model the observed data. Okay, so this was some short introduction into how we can model prior assumptions on properties of processes and functions. And now let us discuss how can we use these to model GP regression. So first of all, we assume that we have a sample of m points. xi is an input vector, multidimensional input vector, and yi is some output label, right? And we assume that our output is equal to the f of xi plus epsilon, where f of x is an unknown function which you would like to recover. And epsilon I is a Gaussian white noise with zero mean and variance sigma squared. And so the function f is and in order to recover function f from these noisy observations, we need to impose assumptions. The simplest, as I said, assumption is to consider f of x to be equal to some linear regression. But in our case, we consider f to belong to the class of Gaussian processes with some smooth covariance function. And so because of that, f of x, it changes quite smoothly with respect to x, opposed to random variations in noise. And because of that, we can recover that smooth signal from noisy observations y. And so the overall generative process is as follows. We have a set of fixed inputs here, xi. And f of x is generated by some Gaussian process. Here is it. Then values of f of x are generated. And then we observe a noisy version of these values of f of x, right? And so these are our observations, and this is the overall generative process. And so the prior P of f, so f here, f capital, is a set of values f of xi. So f is m-dimensional vector here, containing values f of x1, etc., f of xm. And so because of this prior assumption, P of f is a Gaussian distribution with zero mean and the covariance matrix K given by the corresponding covariance function. Because the noise epsilon is a Gaussian noise, P of y given f, where y is a vector of m-dimensional vector containing observations y sub 1, etc., y sub m. Because of this Gaussian white noise assumption, the distribution of y given f, it is also Gaussian with mean equal to f, because f is fixed, and covariance matrix and diagonal covariance matrix, because it's a white noise, with variance equal to sigma squared. And so, what is also important, we will use this property when we construct the prediction. So what is important is that the unconditional distribution of y, which is, it's a misprint here, it should be only one integrand, df. So p of y is equal to the integral of p of y given f over all possible values of f. And so we just calculate convolution of two Gaussian distributions, which is very simple. And we obtain that the unconditional distribution of y is given by the Gaussian distribution with zero mean and the covariance matrix which is equal to the sum of two covariance matrices, K capital and this diagonal matrix sigma squared. And now let us discuss how we can construct prediction using Gaussian processes. Actually, it's very simple using the property of Gaussian distributions. First of all, let us denote the x by x star, the point at which we would like predict the unknown value of f. So x star is a point, is a new input point, and f star is a value of f of x star, right? And so y star is an unknown distribution, is an unknown output value. It's equal to f star plus noise value. Now let us consider the joint distribution of all observations y, all observations from the training sample, and unknown value f star. Of course, it's the joint distribution of these two things is a multidimensional Gaussian distribution, again with zero mean, and the covariance matrix which has this structure. This covariance submatrix is equal just to the covariance matrix of the y, of the vector y, and we just calculated it here, right? Then this covariance submatrix, it is equal to the cross covariances between f star and the vector y. And so k star is a vector of size m equal to the cross covariances between the new point and the point from the training sample. And this covariance value is equal to the covariance of the value f star with itself, right? And so using this famous formula, dated back to the previous century, we can calculate, which tells us how to calculate the Gaussian conditional distribution of the Gaussian subvector given other Gaussian subvector. So using exactly this formula, we just, instead of these quantities here, instead of mu sub 1, sigma capital 1, 2, etc. So by plugging, instead of these quantities, plugging these quantities here, we obtain the conditional distribution of f star given y. And so conditional distribution of f star given y is again Gaussian, with mean vector mu star and covariance value sigma star, where mu star can be calculated explicitly according to this formula, and covariance can be calculated according to this formula. Here, this is a matrix of size m by m. This is a vector of size m, and this is a vector of size m which depends on the value of x star. So this is the only quantity which depends on the new point. And so, and actually we can represent this value mu star as a linear combination with some coefficients. of the covariance function, of the cross covariances between points from the initial sample and new point x star. We see that this is exactly the kernel-rich regression. So it's a kernel regression because k is a kernel. And parameters of alpha can be calculated by this formula. Besides this quantity, which can be used as a prediction at new points, we also get uncertainty estimate, which can be used as a prediction of uncertainty for the prediction at this point. And of course, this uncertainty estimate is based on some specific Gaussian assumptions, but at least it gives us some understanding on at which points the uncertainty is big and at which points the uncertainty is small. And so at least we can compare uncertainties to select where to sample is better, where it is better to sample to reduce that uncertainty. Here is a particular example. Unfortunately, the resolution isn't as good as I prefer it to be, but still we can see that for this case, where we don't have noisy, where we don't have noise in data, using this formula, we can accurately interpolate sample points. So by blue circles here, I depict sample points. And by this red line, I depict here posterior value. So mu actually is a posterior mean value of the posterior process given observed data. And we see that it's quite, it quite accurately interpolates sample data. And by these dotted and also here I depicted by dotted line here uncertainty estimate of these predictions, which can be considered as a kind of a confidence interval for the predictions. In case the data is noisy, so that means that this value sigma squared here isn't equal to 0. We can obtain also quite accurate predictions, but at the same time we see that uncertainty estimate here is significantly bigger. It's because of the noise in the initial sample. And of course, when I was calculating these plots, I assume that I know this sigma value. But in practice, of course, I don't know actual noise variance. And so the question is how we can tune parameters of this model. Because even in this, although this model is a Bayesian model, it's in some sense non-parametric, but still we have some hyperparameters in it, namely parameters of the covariance function and noise variance. And in a minute, I'll explain how these hyperparameters can be obtained. In this picture, I just depicted a typical predictions we can obtain when using different covariance functions. And so for the same data set, you see that depending on which covariance function I use, I can obtain quite different predictions. And so that means that it's very important to accurately select the type of the covariance function and its parameters. And the question is how to do it. And so, because in this case we have a generative model, the generative model of the for the data, which is Gaussian. we can use this generative model to construct a likelihood which we can optimize to estimate parameters of the covariance function and parameters of the noise process. So let me remind that actually the unconditional distribution of the observed output values, this unconditional distribution is Gaussian with zero mean, and covariance matrix equal to the sum of the Gaussian process covariance matrix plus the diagonal covariance matrix of the noise process. Actually, this property, which follows from our prior assumption, this property can be used to explicitly write minus log likelihood. Because this distribution is Gaussian, this minus log likelihood is given by this formula, where C capital is a sum of these two covariance matrices. And so we can explicitly optimize these functional with respect to parameters of the noise process. In this case, it's a variance, and with respect to the parameters of the kernel function, to obtain estimates of these parameters. And so, moreover, thanks to the explicit formula, I can even obtain explicit formulas for gradients of the minus log likelihood with respect to all unknown parameters. And so I can use gradient descent to optimize this minus log likelihood. The main problem here with optimization and the construction of the model is that calculation of all these quantities requires m to the power 3 computations. Because this matrix should be inverted, and the matrix C, it has size m by m. And because of that, it's quite computationally intensive if your sample size is more than several thousand. But nowadays, there exist a lot of approximation tricks how we can approximate and decompose the matrix C using various random Fourier features, special quadrature-based formulas, so that the overall computational complexity reduces to linear, almost linear. And still we get nice properties of the Gaussian process regression, because still it stays quite flexible nonlinear model. And now let us discuss how this model can be used for Bayesian optimization and what benefits we can get from uncertainty estimate. So actually in practice, there are a lot of problems where we need to optimize complex black box functions. For example, so we have some function f of x, and this function is multimodal. Moreover, this function is very expensive to evaluate. That means that it may take hours, even days, to calculate just one value of this function on some high-performance computing device. And that means that we can't perform random search. We can't calculate gradients of this function numerically. And this situation is quite typical for many real-world problems. For example, if we consider engineering optimization of structure of the passenger aircraft, then the whole structure of the passenger aircraft contains thousands of parameters, and just one simulation of the structure may take up to several hours and even days on a cluster. And if you would like to optimize geometry of that structure to minimize the mass, given that the strength of the structure is significantly big, then it is very time consuming and computationally intensive, because on each iteration of the optimization process we will have to perform physical simulations. Another typical situation is modern deep neural networks. So in this case, so let us assume that we have some neural network like ImageNet, which is trained, say, on some big data set like ImageNet. And that neural network is defined by a set of hyperparameters, like number of layers, regularization coefficients, learning rates, etc. So X, although X in this case isn't very high dimensional, it contains like maybe tens of parameters. But still, in order to estimate predictive accuracy of this neural network for the given values of hyperparameters for the given architecture defined by these hyperparameters, it may take a lot of time if the sample is big, because we will need to perform cross-validation and other things. Moreover, in this case, you can't even calculate numerically gradients of that performance with respect to these parameters, because many of these parameters are just discrete parameters. And so the question is how to optimize performance to achieve the best possible with respect to all possible values of hyperparameters. And as I said, there are a lot of real-world applications related to various engineering simulations and optimization of various engineering devices, where we have exactly the same problem with complex simulations. And so the question is how we can perform optimization in this case. And the idea is quite simple. Let us assume that, okay, and of course, here I will just show you some one-dimensional examples. So, and the idea is quite simple. We have some function f of x. So x here is one-dimensional. And we observe just some values of this function. Say, we already have 4 observations. And then, given these 4 observations, the question is where the optimum of this function is located. Well, in principle, the function can go through these points like this. And in this case, actual position of the minimal value of the function is here. But at the same time, it could be other functions with such observed points. And so for these possible trajectories, positions of their minimal values are here and here. The more possible trajectories we can draw through these observed points, the more different positions of local minima on these possible trajectories we obtain. And so here by these columns I just depict possible positions of local minima. And so this is here I have even more trajectories going through these points. And in the limit, we obtain, of course, some Gaussian process. And because of that, we use some Gaussian model to Gaussian process to model these steps. This is posterior distribution of the Gaussian process given these observations. And this is posterior variance given these observations. And you see that, and here I depicted distribution of possible locations of the minimal value of the unknown function. And we see that exactly in this here, it is the highest possibility that the minimal value is located here. And so the overall idea of all these approaches to Bayesian optimization, the overall idea is as follows. We impose some prior assumption on the function we would like to optimize. We sample some values of this function. We calculate posterior distribution of the position of the minimum of the function given these observations, and then we iterate. And as soon as we calculate posterior distribution of the minimum, we can sample around that possible position of the minimum value or some other extremum value of the function. And then we add these new observations to the sample and iterate. What is important is that in this process, we need to support two things. We need to support exploration, and we need to support so-called exploitation. Because, and what is it? So exploration, it is the process when we would like to explore those parts of the input domain where we have the highest uncertainty. And exploitation, it is the process when we would like to better investigate those parts of the input domain where existing model indicates that the optimum is located there. And in case of the Gaussian process prior assumption, that means that we can perform exploration if we consider those points for which uncertainty prediction is big. Because if uncertainty is big, then possibly in that region something interesting is located. And concerning the exploitation, we just need to explore those points for which the posterior mean provides some extremum values, some extremum prediction. And let us consider some heuristic criteria which we can use to sample points. Actually, all these criteria which I will discuss now, they are based on very simple ideas. At the same time, there are papers that prove that under Gaussian assumptions, that is, if the real function, if the real black box function is generated by some Gaussian process, then if we use the criteria I'm going to talk about, then the whole overall process will converge in a finite number of steps to the global optimum. Of course, the speed of convergence is very low, and it is tremendously lower than for typical gradient descent optimization methods. But still, these are some guarantees that the overall process will stop in a finite number of iterations in some reasonable place with better value of the target function. And okay, now let us discuss briefly which criteria we can use to sample points. So again, the overall process is as follows. First, we take the black box function. Then we sample some values from that black box function just randomly, because we know nothing about the black box function, and because we know nothing, we just need to get some information about its behavior. And so we sample some values of the black box function, get some initial sample. Using this initial sample, we construct Gaussian process regression to approximate the black box. Then, using one of these criteria I'm going to talk about, we select the next point at which we evaluate the black box function value. Then, either we stop the overall process because our budget is already finished, or we evaluate at this new point the real function value, add this point to the sample, recalculate the approximation, and iterate. And so let us consider different criteria we can use to select the next candidate for evaluation. In this case, I put here minus mu because I maximize this criteria. All these criteria, they are called acquisition functions. And so, actually, of course, if I would like to find the real minima of the function, and I have some prediction of its value, then I just need to select as a candidate of the next point. I can select such point at which this prediction is as small as possible. That is, I select such x for which this mu of x is as small as possible. However, because this prediction has some error, we need to take into account this error of prediction. And in order to take into account this error of prediction, I just add here the uncertainty estimate sigma of x with some coefficient zeta. And actually, this can be considered as a kind of confidence interval for the prediction of the mean value. And we see that exactly here I have two terms. One term is responsible for exploitation, and this term it is responsible for exploration. Because when I will optimize this acquisition function with respect to x, this will result in some point which either corresponds to the minimal value of mu of x, or which corresponds to the point x at which this posterior variance has big value. And so this is exactly exploitation trade-off which we need for efficient selection of the candidates for the next step. And in case of Gaussian process regression, here we see how this acquisition function looks like. And so we see that its highest value is given here, and we will select this value here for the next, as a next point to evaluate the function value. Also, in applications, they very often use so-called expected improvement. So actually expected improvement is a probabilistic criterion which estimates the average value of improvement over existing observations. So let us define by y best, the best value of the function observed so far, right? And so using all observed values, we constructed the approximation. And then we compare the best observed values, the value mu of x, it's a prediction, with the best value observed so far. And we would like this the actual value of the function to be as small as possible compared to the observed value of the process. So we would like to actually to minimize this difference. But because the actual value of the process, it is uncertain, right? But we know posterior distribution of this value of the process at new point x star. So we calculate a maximum between 0 and this difference, because actually if this difference is negative, we don't care about this difference. But if this difference is positive, then this is very good. And we would like to maximize this. And so we calculate maximum between 0 and this difference, and average it with respect to the posterior distribution of y star given x. X, it's a point at which we observe this y star. And the p of y star given x is a posterior distribution of the process given all existing observations. This integral can be calculated explicitly. And we obtain this formula where f capital is a cumulative density function of the Gaussian distribution, and the function phi here is just a Gaussian density function. And so we can easily maximize this acquisition function with respect to x and obtain the candidate for the next step, right? What is important is that although the calculation of the real function value on each step of this process could be very time-consuming, the optimization which we use to maximize this acquisition function, it is very fast because the acquisition function is some analytical dependency, and it is given by an explicit formula, and we can easily calculate it, we can easily differentiate it, and optimize using any gradient descent algorithm. So it's very fast. And then we obtain candidates. So in this case, this expected improvement criterion looks like this. This candidate is located here, and you see that the possible position of the minimal value is given here. And then we iterate. Another also quite widely used criterion, it's called the maximum probability of improvement, also very simple. As I said, all these criteria, they are just based on, in general, they are based on, like very engineering ideas. Common sense, I would say. So we define gamma of x by gamma of x a normalized value of the process. So we define the distance between, we calculate the difference between mu of x and the best value of the process observed so far, and normalize it with respect to the posterior variance. And actually, we would like to find such candidate input x, such that the value of the process f of x is as small as possible compared to the value of the process observed so far. And we would like the probability of this event, that this event happens, we would like this probability to be as big as possible. And so, but thanks to the property of the normal distribution, because given the observed sample, the distribution of f of x is Gaussian with the posterior mean equal to mu of x and the posterior variance equal to sigma of x. This probability is, can be calculated according to this formula, very simple. Phi capital is a cumulative density function of the Gaussian distribution, and gamma of x is given here. And so the result is, of course, for this very simple one-dimensional case, the result, how this acquisition function looks like, the result is quite similar to what we observed here. So in principle, we will obtain the candidate input for the input value. This candidate will be located quite close to the candidate obtained when we use this acquisition function. But this is only because this example is one-dimensional and very simple. Of course, in practice, when we consider some more complex cases, some multidimensional cases, in those situations, the difference between different criteria will be more significant. And actually, all these criteria, they converge, according to the theoretical results, they converge more or less with the same speed in the limit to global optima, but in practice, usually the people use expected improvements. In papers, they claim that usually it is more computationally efficient. I mean, sample efficient. And of course, there are a lot of generalizations. So I just described very basic things. And in practice, the data can be of different fidelities. Then actually, the data can have heterogeneous noise, how to select kernel, how to select hyperparameters on each step of this process. So actually, there are a lot of research questions, and still this topic is quite popular, and there are papers on conferences devoted to these algorithms. And so, finally, instead of optimizing the initial function, which is very inefficient, we construct some acquisition function, which on each step depends on the existing, on the obtained sample of the initial function. We use this acquisition function to sample the next input. Solving initial optimization problem, which is quite difficult, we can perform this Bayesian optimization. And actually, for applications, this very often this is enough, because we don't need to find global optima. For engineering devices, you just need to find some better design compared to the existing one. Say you need to improve for 10% some property, and that's it. And because of that, you don't need to find global optima. You just need to sample the next design of your object as fast as possible. And so this type of approaches, in some cases, they can help to do it quite efficiently.
And now let us consider how these approaches can be used to tune hyperparameters of the old school SVM approach. I guess all of you know what is support vector machine. And so we would like to tune hyperparameters of the SVM classifier. In this case, I consider a very simple artificial classification problem generated by scikit-learn routine. So this problem contains 2,500 samples. The input dimension is 45. So due to the input dimension is 45, and among these 45 features, only 15 of them are informative and actually informative. What is important is that we would like to optimize performance of this classifier with respect to two hyperparameters of the support vector machine. The first hyperparameter is C, where it's a penalization for slack variables, and gamma is a kernel width. And as a target function, we optimize with the accuracy on the ROC curve. And this accuracy on the ROC curve is estimated using three-fold cross-validation. And because of that, even with this not very big classification problem, it is quite time consuming. So you need to wait for maybe for 1 or 2 minutes in order to estimate value of the accuracy on the ROC curve for a given value of x of these two hyperparameters. And let us consider whether we can really obtain, whether we can really apply Bayesian optimization to select these hyperparameters. And so this is how accuracy on the ROC curve depends on this hyperparameter. So I just pre-computed for all possible values of x, it's dependent, the dependence of accuracy on x. And we see that the real optima is located somewhere here. And this is the first parameter C, and this is the second parameter gamma. And these are actually, by colors, I depict here actual values of this accuracy under a curve. And so, as I said, optimum value is located somewhere here. So what I did, first, I just sampled several values of C and gamma randomly. And for them, I estimated the value of under the ROC curve. These values are given here by these three blue points. And then, by star here, I depicted the position of the real optima. And then, using these three values, I constructed a Gaussian process. And so, by these colors, I depict how this Gaussian process regression constructed using only these three values, how it looks like. And so we see that, of course, it doesn't resemble very good the actual behavior on of the accuracy on these hyperparameters, but actually we only have 3 observations. Anyway, For this Gaussian process regression, I calculated expected improvement criterion, and we see how this expected improvement criterion really looks like. And we see that optimum of this expected improvement criterion is located here, right? And so we optimize expected improvement criterion and obtain the point for the next step, which is located here, because expected improvement has the highest point here. Then we sample a real value of the accuracy on the ROC curve at this value of C and gamma. Here is it. Then we reconstruct Gaussian process regression. Now it's looked like this. It is based on 4 observations, 1, 2, 3, and 4. Then for this Gaussian process regression, we construct expected improvement. And we see that its optimum is located here. And then we add this new observation and construct Gaussian process regression again. Now it is look like this, and this is how expected improvement looks like. And after like its iteration number 5, I guess it's iteration number 6, right? So overall, I did 9 so I did 9 iterations, because initially I draw 3 randomly values. I draw 3 values of C and gamma randomly, and then I did 6 iterations additionally. So overall, I did cross-validation 9 times. And we see that after 9 iterations, already the expected improvement based on the Gaussian process looks like this, and its optimum is very close to actual position of the optimal value of the hyperparameters. So that means that in principle, after 9 iterations, I already quite close to the optimal value of hyperparameters. And if I just randomly, and it's obvious that if I just randomly sample 9 values of C and gamma, or I consider grid of values of C and gamma, I will not get as close to this optimal value as I get to it right now, thanks to expected improvement. And if I continue this process, so if I continue sampling these Gaussian process and obtaining expected improvement, optimizing expected improvement, and adding points to the sample where the expected improvement is high, then my points optimum of that expected improvement will be very close to the actual optimum value of the accuracy under ROC curve. And so we see that the more iterations we do, we just start to to jump in some small neighborhood of the real optimum. So this is the typical illustration of how expected improvement behaves. And just some messages. So what I want to say. Gaussian processes, they are quite simple to use. Not many parameters. You can estimate uncertainty, and although now deep neural networks are very widespread and you can solve a lot of problems with them, still people continue to use Gaussian processes in many applications. Moreover, there are approaches how to calculate so-called deep Gaussian processes. although there are some discussions on whether they are more useful and why they are more useful than neural networks, but still you can consider not only deep neural networks, but deep Gaussian processes as well. And as I just showed, in many applications, these Gaussian processes can be very useful when you need uncertainty estimate. What else? I still have like 10 minutes, so I think I'll use 5 more minutes for discussing a little bit more advanced topic, and then we will have some small time for questions. So after these presentation, I think you can download the slides. So in back slides, you can find some additional interesting topics, which I mentioned if you would like to consider Gaussian processes which are scalable, or to consider non-stationary Gaussian processes, because you can see in all these examples, I mainly consider the case when the covariance function depends on the difference between input arguments. So that means that actually this function is stationary. But in many cases, we should model non-stationary phenomena, and then for that we need to use special tricks. And so this you can find in some back slides of this presentation. And now I would like to discuss with you some related to Bayesian optimization, Bayesian regularization. Actually, with Gaussian processes, it's not so when you tune parameters of the covariance function, it may be not so stable. Of course, you can tune those parameters not very accurately, just consider some grid of values to tune those parameters theta here. But in multidimensional case, it's not very efficient. But when you apply a gradient descent to tune these parameters theta here, it may happen that due to numerical instability, these parameters can diverge to some not very good values because the log likelihood actually it is multimodal function. And here there is a particular example of such situation. So this is the function we would like to approximate, and just to obtain, and in order to illustrate the phenomenon, I consider the training sample of quite small size, which is not sufficient to recover this complex function. But still, let us try to feed the Gaussian process using this small sample. And the result I can get is very bad, actually. So actually, these peaks here, these are posterior mean I obtain because when I optimize the log likelihood with respect to these parameters theta here, after optimization, I obtain very big values of theta. And so because of that, the final posterior approximation I obtain, it looks like this. So it just not very good approximation. Now, another problem, another kind of opposite case can happen when we optimize the log likelihood, and as a result we obtain parameters theta which are very small. For example, if we this is the function we would like to approximate, and when we feed the Gaussian process to this function, we obtain this approximation. It looks reasonable, but if we zoom some part of this function, we see that it looks like this. And so it is very numerically unstable. And it is because the corresponding covariance matrix is almost ill-posed, since the parameters theta, they are very small. And the question is how to deal with these two divergent cases. The idea is to impose Bayesian regularization. And that is quite simple, but it's quite efficient. So we assume the parameters theta inside the function, they are random variables by themselves with gamma distribution with some prior parameters alpha and beta. And so, log likelihood of these parameters theta then is given by this formula. So this is just log prior distribution on parameters theta. And then the overall log likelihood for the data given observations and parameters, it will consist of two parts. The first part is the log likelihood from the Gaussian distribution, and the second part is log likelihood from these gamma prior on parameters. And then we optimize not only with respect to parameter theta, but also with respect to parameters of the gamma prior distribution. So actually, this is a kind of map Bayesian estimate. And you see here that thanks to this structure of the gamma distribution, because we have this term here and this term here, the parameter theta can't be too big and it can't be too small. So we penalize both cases. And if we apply if we train hyperparameters of the Gaussian distribution using this procedure, instead of, as a result, instead of this posterior approximation, we obtain this quite nice approximation. Of course, it's not accurate, but still it's numerically stable, and it resembles the initial function which we would like to recover. The same situation is with this noisy approximation. So initially it was like this, but after this regularization, when we approximate this function and zoom some part of this function, we obtain already quite nice posterior approximation. And so these are just two examples showing that although to construct the Gaussian regression, we just need to remember a simple Gaussian theorem about conditional distribution of Gaussian subvector given another subvector. Still, there are some hidden complexities, I would say, which we need to know when we apply all these techniques in practice. That's it. So this is what I would like to discuss with you today. After this lecture, it will be a coffee break and a seminar by Yermek Kapasho, who will discuss with you different examples, how this can be applied in practice, both regression and Bayesian optimization. So questions, comments, remarks? Yes, please.
Just two technical questions on the process of Bayesian, not Bayesian, Gaussian inference. Well, when we started, we established the model when wait a minute. When the f at x, which is essentially a Bayesian process, is always with mean equal to 0 y. Doesn't it gives us like stable process?
As I said, we just did it for simplicity. Of course, we can, usually in practice, they consider as mean function some parametric function. And then when optimize look likelihood, they optimize simultaneously parameters of that parametric function given the prior mean and parameters of the covariance function. And so simultaneously we can feed the prior mean to the data and the Gaussian process to residuals with respect to that prior mean. But for simplicity, not to overburden all notations, I decided not to consider this thing. Yes, what else?
A naive question. So you showed like Gaussian processes can be used for regression problem on like nonlinear regression problem, and the example you showed, then I saw similar case that used the Gaussian mixture model to do this similar nonlinear regression. So I want to ask, what's the essential difference between Gaussian process model and the Gaussian mixture model to apply these nonlinear regression, and in which case it's better to use Gaussian process, in which case it's better to use Gaussian mixture model?
But as far as I understand you, Gaussian mixture, by saying Gaussian mixtures, they're usually used for clustering. So Gaussian mixture, so those components in Gaussian mixture, they are used to model different parts of the design space, and then each part of the design space can be modeled by its own regression model. So Gaussian mixture model usually, I mean, initially Gaussian mixture model, it's a model for clustering. It's an unsupervised problem. We have only inputs, and we would like to model some points, some clouds of points, and each cloud we model by a multidimensional Gaussian. And so we have several clouds, and we obtain Gaussian mixture model because of that. But this is for unsupervised setting, when we have only clouds of input points. But in here I have supervised setting when we have inputs and outputs. Okay, so what else?
Thank you for your presentation. So when you gave us those couple of examples of covariances, matrices, or kernels, you also showed us the neural network kernel.
Right.
Can you give us a few more words about that?
About the neural network kernel?
Yeah.
Well, in principle, yes. There are nowadays there are a lot of papers that show some relations between simple neural networks, say two-dimensional perceptron, and Gaussian processes. Actually, if we consider a neural network just with two layers, and we assume that parameters of that neural network are distributed with some distributions, and the number of these neurons goes to infinity, then it can be proved that the limiting distribution of the output of that neural network is Gaussian and is given by the Gaussian process with that neural network kernel. And actually, if on some recent conferences you can find papers where they calculate limiting distributions for modern deep neural networks by approximating these distributions with Gaussian distributions with some specific kernel functions. Well, okay, so in the limit, everything converges to normal distribution according to central limit theorem, as you know. Okay.
Right at the beginning, when you were talking about the kernels, you had one slide where you were changing the length scale and then I think the prefactor.
Right.
There was the first figure which showed there were three figures which showed I think the posterior predictive distributions. The first and the last ones were almost exactly the same. Can you go back to the slide and tell what was the difference between the
Okay,
first and the second?
I think I can do it quite fast. This one?
No, a couple more slides back, I guess, where you had like...
Next?
No, a few more slides back, I guess.
This?
You had 3 figures side by side.
3 figures, okay.
This one.
This one?
So the first and the last one look almost the same to me. So I'm guessing there's some difference in the hyperparameters.
Here there are no. I need to check. I don't remember exactly what are the hyperparameters for the first figure and the last figure. Possibly these are two these are two different covariance functions, but with different hyperparameters, such that the result of posterior calculation is similar. This also can happen in principle.
Because then the prior samples, they look to be, they almost have like the same.
Yeah,
landscape.
prior samples are the same exactly. Okay, so it's already almost the time. Yeah, so sorry for that, guys. Maybe one quick question. No?
You can ask questions first.
Okay, so that's it.